Okay, so we're going to do chapters 9 and 10 together. And actually, we're only going to be covering the first two sections of chapter 10. And you also may notice that the order is the order of the slideshow is a little bit different from the way the book is. And part of that is because when I'm teaching this in class, I want to cover certain things before a particular lab, before they get to a particular lab. And so it's still covering all the material, but just in a different order. Okay, so we start with chemical bonds. And we've already talked about them to some extent, but we really haven't talked about how they form or why they form. But let's just talk about the three general types of bonds first. The ionic bond is when there is a charge. There's a difference in charges. There's a positive charge and a negative charge, and then those two ions are attracted to each other. Okay, so ions can be formed from atoms when there was a transfer of electrons, or ions. At some point that had to happen, but you can also get ionic compounds that are already formed ions. And so usually an ionic compound is the result of a metal, because metals tend to lose electrons, with nonmetals. On the far right, so not including the noble gases, but like the halogens and group 6A and some of those in group 5A, the nonmetals, or polyatomic ions. Okay, and then we also have covalent bonds, and a covalent bond is what results from sharing electrons. It's usually it's not able to gain electrons or lose electrons, but instead they're going to share them. So some of our most familiar examples are H2O and CO2. And they are generally the interaction of nonmetals with another nonmetal, so two nonmetals. And then the third kind of chemical bond is actually a metallic bond, which is when two metals are bonded to each other, or just or the way that metal atoms are bonded to each other. And generally speaking, they just are a bunch of nuclei spread throughout the metal, and then the electrons tend to move freely throughout the three-dimensional structure. And so that is what makes metals especially have conductivity. We're not going to focus too much on metallic bonds in this course. So why do atoms form chemical bonds? Well, we know from experience that noble gases are very stable. They don't react with other elements, and they have a very high ionization energy, which means it's very difficult to remove electrons from them. So they're just happy the way they are. And we also know from chapter 8 that all noble gases, of course except for helium, have 8 valence electrons in their highest energy, or their outermost shell. And so 8 seems to be a really stable number. Helium, of course, only has 2 electrons, but it does fill up its outer valence shell. And so again, that seems to be the stability, is that the outer shell is full. Doesn't have too many, doesn't have too few, and for most of them it ends up with 8 electrons. And so the octet rule says that atoms will tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons, or in other words, to correspond to a full s and p subshell for whatever shell we're talking about. All right, so let's look into this a little bit further. A Lewis electron dot symbol is a symbol where we show how many valence electrons are surrounding an atom. So this is pretty straightforward. Sodium, which has 1 electron, we just show with 1 dot. Magnesium or anything in group 2 would have 2 dots, 3 dots for aluminum, etc. It's really not critical that you put them. This is kind of the standard way that we put the electrons in there, but there's no right or wrong way. Usually we put them around first and then go back and pair them. And notice that the group number indicates the number of valence electrons, so that's very helpful. At least the A group numbers. All right, so we're going to start with covalent bonds. So even though chapter 9 actually starts with ionic bonds, we're going to put that off a little bit in the PowerPoint. So when two nonmetals bound, what they do is share electrons. It's because they have similar attractions for the electrons. One doesn't have a stronger attraction for an electron than the other one does, and so they can't really steal the electrons away from each other. And so they share them. So when there is a shared pair of electrons between two atoms, we call that a covalent bond. And the reason why they'll make a bond is that they want to get 8 electrons, and so atoms will share enough numbers of electrons in order to get that 8 valence electrons or noble gas configuration. So some atoms only need to share 1 electron in order to get 1 more, or some have to share more. Okay, so let's look at the simplest example of a covalent bond, which would be a hydrogen molecule with 2 hydrogen atoms. So as the 2 hydrogen atoms get closer, we've got all these interactions. We've got the two positive nuclei, which are going to be repelling each other, and then the 2 negative electrons repel each other also, but they start to attract the positive of one attracts the negative electron of another, and so what happens is the 2 electrons end up being held in between the 2 positive ions. And since electrons have a way of shielding from each other, you know, if they have the different spin that we saw back in chapter 8 and 7, then they can exist next to each other, and they're both attracted to the 2 nuclei, sort of acting like a glue. There actually is, I'll show you the next slide. So this is sort of a quantum mechanic, an equation where they took the probability of where those electrons are, and you can see that the highest density is right between the 2 nuclei, the 2 positive nuclei. So most of the electron density is between the 2 hydrogen. So the electrons sort of act as a glue that holds the hydrogen atoms together. All right, so we just saw that the density concentrates between the nuclei. Overall, the net attractions are attractive, and so the 2 positive nuclei are attracted to the negative charge in between, which acts sort of like a glue. Okay, we can represent this bond in this way. So if we take our 2 Lewis dot structures, our hydrogen atom with 1 electron and another hydrogen atom, and then we put the 2 dots between the hydrogen, that represents a bond holding the 2 hydrogen together. So 2 dots generally represent a covalent bond. A lot of times we'll put a dash in place of 2 electrons. So here's just another, the 2 electrons really spend part of the time in the region around each atom, but it's pretty much in between, and so those 2 electrons really belong to both atoms. And so each hydrogen has 2 electrons that it gets custody of, and so it acts like it has a helium configuration, which is sort of the goal. It wants to, excuse me, it wants to have the noble gas configuration. Okay, in a similar way, we can bond a hydrogen and a chlorine together to give an HCl molecule. So in this case, however, chlorine has 7 valence electrons and hydrogen just has 1. So if hydrogen and chlorine share those 2 electrons, the chlorine now is happy to have 8 electrons and hydrogen has 2. And so again, they act like they're noble gas. So chlorine has the 8 valence electrons, similar to argon. Okay, and so these are called Lewis dot structures, or Lewis dot formulas. I usually call them Lewis dot structures. And you need to be able to distinguish between a bonding pair of electrons and a lone pair of electrons, or non-bonding pair of electrons. So I think that's pretty straightforward. An electron pair that is shared would be called a shared pair or a bonding pair, and then electrons that are not shared between 2 elements would be a lone pair or an unshared pair. I use both of those terms pretty interchangeably. Okay, so if you're looking at the periodic table, this is not always absolutely true, but you can often get a good idea of how many bonds that certain elements can make because, they always want to have 8 electrons. Although, like I said, there are some exceptions to the rule that we'll talk about, and some elements can form more bonds than just can actually have more than 8 electrons. But again, for right now, in general, hydrogen, fluorine, chlorine, and bromine like to make one. Well, hydrogen only ever will make one bond because it only needs one more electron. And in most cases, fluorine, chlorine, and bromine only need one more electron. And so they tend to make one bond. Although, like I said, chlorine and especially bromine might make different things. But as a rule, they like to make one bond. Oxygen, which needs 2 more electrons, will tend to make 2 bonds. Nitrogen, which needs 3 more electrons to get the full octet, will tend to make 3 bonds. And then carbon and silicon will make 4 bonds because they need 4 electrons. So it's helpful just to keep in mind later on, especially when you're trying to arrange putting the atoms in a Lewis dot structure. For example, hydrogen should not be in the middle of any 2 other atoms because hydrogen can never make more than one bond. And the same thing generally with fluorine, chlorine, and bromine. They like to be on the outside of a molecule because they only make one bond each. Oxygen needs to have 2 bonds and nitrogen needs to have 3, etc. Okay, we can have actually multiple bonds. So far, we've been talking about a single bond, which is just one pair of shared electrons. It's also possible to share more than one pair, and so a double bond, in fact, is where 2 atoms share 4 electrons. We can also have a triple bond where 2 atoms are sharing 6 electrons or 3 pairs. So a pair makes 1 bond, and we can have more than 1 bond. But remember that they never want more than 8 electrons as a general rule. Again, there are some exceptions, but they can notice that all 6 of these electrons now belong to both carbon, so carbon still has its 8 in both cases. And in a little while, we're going to talk about Lewis dot structures and how to draw them and how to come up with those structures. All right, first though, let's talk about what is a polar covalent bond. Okay, so a covalent bond, again, is one where electrons are shared, but a polar covalent bond is one where they're not shared equally or not evenly. So generally speaking, the electrons spend more time near one of the 2 atoms involved. So it has to do with how much atoms like to have it's sort of like a tug of war for the electrons. So if the 2 atoms involved in a bond are the same, so like a HH bond or a CC bond or an FF bond or whatever, if the 2 elements are the same, that means that the electrons will be shared equally because one atom doesn't have a stronger attraction to the electrons than another atom. So that's generally, we would call that a nonpolar covalent bond because there's an equal sharing of electrons. However, if the 2 atoms are different elements, and that the difference between how much they like electrons is different enough, then we have what's called a polar bond or a polar covalent bond. I think we'll see that in the next slide. Let's look at some examples. An OH bond over here is considered polar, and it looks sort of like this. The oxygen has a stronger pull on the electrons. It likes electrons more, and so the electrons actually spend more time over on the oxygen side, and you can see the electron density is greater on the oxygen, whereas a CH bond is considered nonpolar because really the electron density is shared equally by the 2 atoms involved. So we call the OH bond a polar distribution and the CH bond nonpolar. And so what happens, and because the electrons are more toward the O, that makes the oxygen a little bit more negative than the hydrogen, and so we say it's got a partial negative charge on the oxygen. We give the symbol delta negative, meaning a partial. It's not a full-blown charge, but partial. And then a partial positive charge on the hydrogen. Okay, so electronegativity is a measure of the ability of an atom to draw bonding electrons to itself. And we looked at that a little bit in chapter 8. In general, electronegativity increases from the lower left-hand corner to the upper right-hand corner of the periodic table. Something that has a higher electronegativity is more of an electron hog. It likes to hoard the electrons or pull it closer to themselves. There's actually values assigned to every element on an electronegativity scale. The value of 4.0 is given to fluorine, and then other elements were measured in relation to that, and so the smallest value is 0.7, and I think it's on the next slide. So yeah, this is the electronegativity. You can see fluorine has the highest electronegativity of any element, and then oxygen is very high too, and nitrogen and chlorine are all very high. So the upper right-hand corner tends to have the highest electronegativity, and the lower left-hand corner has the lowest electronegativity. So what do these numbers mean? Well, it's sort of a relative a comparison of which atom likes the electrons more. So if you take the absolute value of the difference in electronegativity of two bonded atoms, then it gives you a good idea if the bond is polar or not polar. So if the difference between the two numbers is small, in other words, less than 0.5, so we're gonna make the dividing line. If it's equal to 0.5, it goes with the next category. But if it's less, so if it's 0.4 or less, the bond is considered nonpolar. If the difference is bigger, so if it's equal to 0.5 or greater, we call it a polar bond. And actually, since chemistry is more of there's not just black and white, it's usually more of a continuum. We actually, if the difference exceeds around 2.0 to 2.1, the sharing is so poor. One atom likes the electron so much more than the other that in fact the one that likes electrons more will actually steal the electron, and so you actually have an ionic bond. So again, you've got this sort of spectrum. So you've got, if they're very similar, we have a nonpolar bond. If they're pretty different but not too different, then we have a polar bond. And then if the difference is really large, then we have an ionic bond. So let's look at some examples. I said this earlier, if you have a bond between the two same elements, it should be nonpolar because they share electrons equally. Well, and then if you take the difference between the electronegativity, so the absolute value again, so we never use negative numbers, just always take the bigger one minus the smaller one. And since Cl and Cl both have the same value, the difference is 0. So of course, anything less than equal to or less than 0.4 is considered nonpolar. And they have an equal sharing. An HCl bond, if you look up the value, Cl is 3.0, hydrogen is 2.1, and so the difference is 0.9, so that's considered polar covalent, and it's got an unequal sharing. Now, it actually turns out, how can you tell which one likes electrons more? Well, it's the one that has the higher number. So since chlorine has the larger number, the chlorine will be the negative end and the hydrogen will be the positive end. The bond between lithium and chlorine is so different, 3 minus 1 is 2.0, that we pretty much consider that an ionic bond. And so there's not even any sharing of electrons. The lithium has totally given up the electron and chlorine has totally grabbed the electron. So a polar bond then we know has a positive end and a negative end, which is called, it's a separation of charges, and we call this a dipole. Or the quantitative measure of a dipole is called a dipole moment. So there's actually, depending on how different the two atoms are in electronegativity, the larger the dipole moment. Dipole moments have both magnitude, like an amount, and also a direction. So generally, the dipole moment, you could say, it kind of pulls the electrons toward the negative end. Then the important thing, why do we need to know about polar molecules, is that they will tend to align themselves with one another. So you can see in the picture over here, the chlorine, the negative end is attracted to other positive ends of other HCl molecules, and the positive end is attracted to other negative ends. And so this will be really important, something important for all properties of molecules that we will talk about in future chapters. So, the stronger the attraction between molecules, the harder it will be to pull them apart. And so it will make a difference in terms of boiling points or melting points or how things dissolve in other things. So this is really an important thing to understand now because we use it again a lot in the future.